Ever wondered how we can possibly understand something as massive as the entire stock market just by looking at a tiny little piece of it? Well, that's the whole game of statistical inference, and today we are going to break down exactly how that magic works. I mean, you've seen this a million times, right? A poll of just 1,000 people claims to know how millions are going to vote. It sounds kind of crazy, almost impossible, but the logic behind it is actually incredibly powerful and, believe it or not, surprisingly simple.
And that logic? It's the exact same one you use every time you're in the kitchen. If you want to check the seasoning on a big pot of soup, you're not going to drink the whole thing, right? No, you take one little spoonful. And if you've stirred the pot well, that one spoonful tells you everything you need to know.
Okay, so let's translate that into stat speak. The entire pot of soup, or say the entire stock market, that's what we call the population. It's the whole shebang, everything we want to understand. And that single spoonful we taste, that's our sample. Just a small piece that we use to learn about the whole thing. Now, here's the most important part. The true saltiness of the entire pot of soup, that's a parameter. It's a true characteristic of the whole population. Problem is, we can almost never measure it directly. So instead, we measure the saltiness of our spoonful. That measurement, that's a statistic. And the entire goal here is to use that statistic from our sample to make a really good guess, an inference, about the true population parameter. Of course, this whole idea completely falls apart if our spoonful is, well, a bad spoonful. You know, if you just skim the top and get all broth, or scrape the bottom and get a chunk of carrot. The quality of your guess is 100% dependent on the quality of your sample. Garbage in, garbage out. So, in statistics, how do we make sure we stir the pot properly? We use probability. Methods like simple random sampling, where everyone gets an equal shot, stratified sampling, where we sample from different subgroups, and cluster sampling are all designed to give every single member of the population a fair chance of being picked. This is how we avoid bias and get a spoonful that actually tastes like the whole soup. And this isn't just some abstract textbook theory. This is absolutely fundamental to how modern finance works. Just think about a big bond index. It could have thousands of different bonds in it. There's no way a fund manager can go out and buy every single one. It would be a logistical and financial nightmare. So they have to rely on a really clever way of sampling. And this is where stratified sampling becomes a superpower. First, the manager chops up the entire bond universe into different groups, or strata, things like how long until they mature, their credit rating, and what industry they're in. Then they take a small random sample from each of those buckets. They make sure the proportions in their sample match the proportions in the big index. And what do they get? A small, easy-to-manage portfolio that behaves almost exactly like the huge, complicated index. It's brilliant. So just to quickly recap these methods, you've got simple random, which is great when your population is pretty much all the same. Then you have stratified, which is perfect for diverse groups, like our bond example, where you need to make sure you get a little bit of everything. And finally, cluster sampling is your go-to when your population is spread out all over the place, because it lets you sample whole groups at a time.
Now, in a perfect world, we'd always use what's called probability sampling. The idea here is simple. Every single member of the group we're studying, every stock, every customer, has an equal and known chance of getting picked. That's the gold standard. But let's be real, in the fast-paced world of finance, we often turn to non-probability methods because they're faster and cheaper. And that's exactly where the danger starts to creep.
Probably the most common shortcut you'll see is convenience sampling. And it's exactly what it sounds like. You just grab whatever data is easy to get your hands on. It's fast, it's cheap, but the huge glaring downside, that sample might have absolutely nothing in common with the population you're actually trying to understand.
Next up, you've got judgmental sampling. This is where an expert basically uses their gut, their professional experience, to handpick the data. Now, this is a real double-edged sword. On one hand, it can be super efficient. On the other, you risk baking that expert's personal biases right into your analysis from the very start.
But here's the thing, even if you nail your sampling method, there's this hidden trap waiting for you. And honestly, it's so subtle that it can make your entire analysis completely worthless, even when you think you're making it better.
So let's walk through an example. This one's a classic from the curriculum. Picture this. It's year 1, and you've got an investment manager who's playing it super safe. Their strategy is conservative, which means their returns have a low average and, really importantly, low volatility. So their returns chart looks something like this. See how everything is packed together? No crazy highs, but no devastating lows either. It's predictable. Okay, but then comes year 2. The manager decides to completely switch things up. They're going for the big bucks now, which, as you know, means taking on a whole lot more risk. This isn't just a small tweak. They have fundamentally changed the population of returns they're drawing from.
And just look at the chart for year 2. It's way more spread out. Yeah, you've got the chance for bigger wins, but you've also got the chance for much bigger losses. And this is where that hidden trap I mentioned comes into play.
Because if some analyst comes along and thinks, hey, I'll just combine both years to get a bigger, better sample, they've just walked right into it. That combined data, it's a mess. It doesn't represent the old conservative strategy, and it doesn't represent the new aggressive one. It's a Frankenstein's monster of data that literally represents nothing that actually exists.
All right, so we've stirred the pot and we've got ourselves a good representative sample. But how can we be sure? How much confidence can we really truly have in that single spoonful? Well, this is where we get to one of the most beautiful and powerful ideas in all of statistics. Because let's be real for a second. Even if you do everything right, there's always a tiny chance you just get a weird spoonful, right? A spoonful that's just a little too salty or not salty enough just by pure random luck. So what protects us from these flukes? The answer has a pretty intimidating name: the Central Limit Theorem, or CLT for short. Now, I know this definition looks like a wall of text, but I promise you the idea behind it is pure elegance. Let's just break it down. Okay, here's what the Central Limit Theorem really means, in plain English. Imagine we took not just one, but thousands of spoonfuls from that soup. And for each spoonful, we measured its saltiness. The theorem says if you plot the averages of all those different samples, they will always form a perfect, predictable bell curve. And here's the truly mind-blowing part. This happens no matter what the original data looked like. It could be lumpy, it could be weird. The distribution of the sample averages will always make that beautiful bell shape. Let's actually watch this magic happen. So here we've taken a bunch of really small samples, just 10 items in each. If we plot the average of each sample, well, it's kind of messy, right? It's all over the place, no clear shape yet. But now look what happens when we increase our sample size to 50. We do the same thing, take thousands of samples, plot their averages, and whoa. Okay, a shape is starting to emerge. It's clumping up in the middle, getting more symmetrical. You can see it starting to happen. And finally, with a sample size of 300, boom, there it is. A near perfect bell curve, exactly like the theorem said would happen. It's this beautiful, predictable shape that gives us the power and the confidence to make guesses from just a single sample. So what's the magic number for this to kick in? Well, the general rule of thumb you'll see all over finance and statistics is a sample size of 30 or more. Once you hit n equals 30, you can generally assume the central limit theorem is doing its thing. Now, because we have this predictable bell curve, we can calculate something incredibly useful, the standard error. This tells us exactly how precise our estimate is, how spread out those sample means are. And just look at the formula. That little n on the bottom is key. The bigger your sample size gets, the smaller your standard error becomes. That means a more precise estimate and more confidence in your result. The central limit theorem is an absolute pillar of statistics, but it does kind of rely on this idea of taking lots and lots of samples. So what happens in the real world, where you're often lucky to get just one? Well, this is where modern computers give us a kind of statistical superpower. Let's go back to our soup. Imagine you took your one spoonful, and then the kitchen closed. That's it. You can't go back to the pot. All you have is that single sample in your hand. How on earth can you figure out your standard error now? The answer is a really clever technique called bootstrapping. Bootstrapping is an amazing computational trick. You start with just your one sample. Then you tell a computer to create thousands of new resamples by drawing from your original sample, but, and this is the key, with replacement. You just keep doing that over and over, calculating the mean each time. After you've done this thousands of times, you get a whole distribution of these resampled statistics, which lets you estimate the standard error, all from that one single original sample.
And it actually works. As the CFA Institute puts it, the whole process works because you're treating your one good sample as if it were a mini version of the entire population. Since a good random sample should look like the population anyway, this simulation gives you remarkably accurate results. And that brings us to a final, pretty mind-bending thought. Techniques like bootstrapping mean we can basically simulate thousands of what-if scenarios, thousands of alternate realities, all from a single set of data. It really leaves us with a huge question for the future of finance. In an age with this much computing power, what other problems that we once thought were impossible are now suddenly within our grasp?